Hello students, in this video we are going to learn about Bohr's second postulate, which is in atomic physics. So let's go to the explanation. It defines the stable orbits. What is stable orbits? Stable orbits means electron can revolve only in certain discrete non-radiating orbits called stationary orbits. Means, see here, this is the nucleus. So around the nucleus electron is rotating. So this is the electron. So the distance between from nucleus to the electron is r. With the velocity, the electron is moving with the velocity v. Is it clear? Now it defines the stable orbits. The stable orbits means electron, see I am writing here, electron can revolve only in certain discrete non-radiating orbits. Is called stationary orbits or stable orbits. So here, for which the stationary orbits, for which here total angular momentum is an integral multiple of h by 2 pi. See, I am going to explain it clearly. So Bohr's second postulate defines stable orbits. Stable orbits definition is electron can revolve only in certain discrete non-radiating orbits, that is called stationary orbits. Here, for which total angular momentum is integral multiple of h by 2 pi. That means here electron is rotating around the nucleus in circular motion. For every circular motion orbit, we have circumference. So here we can say that the circumference of the orbitals must be equal to the integral multiple of its wavelength. See, actually this is the original nucleus and the electron is rotating around the nucleus. Behind this, the original nucleus is like this. See, we can imagine like this. So this is here. Before going to know about this point, we must know what is wavelength and how we can calculate the wavelength. See, this is the, see I am writing here, this is the point that I am taking, one crest and one trough. So this is, we can say that positive half circle and this is a negative half circle. So the length between the positive half circle and negative half circle is nothing but, this length is nothing but wavelength. Is it clear? This is the wavelength. So in this topic we have so many crests and so many troughs. The original image is like this. So in the waveform it is rotating around the nucleus. Here we have so many crests. This is a one orbit and this is another one. See, I am writing with the dots. See, so the distance between the one half circle, that means one crest and one trough, is the one wavelength. Here we have so many wavelengths. This is one wavelength and this is the distance between one wavelength, and this is the distance between another. Like this we have so many wavelengths for a single orbit. Is it clear? So the circumference of the orbits must be equal to the integral multiple of wavelength. It is nothing but wavelength. This is the wavelength. See, I am writing here. What is the angular momentum here? That is, here the circumference of the orbital is 2 pi r. See, here I am writing circumference of orbitals is 2 pi r. 2 pi r is equals to the integral multiple of its wavelength, that is lambda. The integral multiple means here I am taking n orbitals. If I am taking one orbital means I can write it as 1 lambda. If I am taking two orbitals, that is we can write it as 2 lambda. But here we are taking it as multiples of its wavelength, integral multiples of its wavelength. So I am writing it as n lambda. Is it clear? So let's take it as a equation number 1. So according to de Broglie, what is the wavelength? Wavelength, that is lambda is equals to h by mv. Is it clear? So let's take it as the equation number 1. So let's substitute this equation number 2 into equation number 1. Then we will get 2 pi r is equals n lambda. In the place of lambda we can write h by mv. Is it clear? So here I am taking mv to this side. That is mv is equals to mvr is equals to and h by 2 pi. Is it clear? This is the angular momentum. Yes or no? Angular momentum. So nh by 2 pi. See, I am going to explain it very clearly. If I am taking the nucleus right here, I am writing this side. You can get the clear idea. This is the nucleus, and around the nucleus I am taking one orbital and second orbital, third orbital and nth orbital. See, this is the nth orbital, and this is first, and this is second, and this is third, and this is nth orbital. Is it clear? In this, an electron can revolve only in those orbits where angular momentum L is equals to nh by 2 pi. Is it clear what I am saying here? See, an electron can only, already told you that in previous, that is electron can revolve only in certain discrete non-radiating orbits called stationary orbits, in which a total angular momentum is an integral multiple of h by 2 pi. Is it clear? See here, where an electron can revolve only in those orbits where angular momentum L is equals to nh by 2 pi. nh by 2 pi. Is it clear? So where angular momentum is nh by 2 pi, those orbits only electron can revolve. Is it clear? This is the main point in Bohr's second postulate. See, whenever we want to check in the first orbital, there we need to check whether the wavelength, that means whether the angular momentum nh by 2 pi is satisfied or not. If it is satisfied, then only the electron can revolve in that particular orbit. Is it clear? So the statement is, you make a note about this point, that is an electron, see here I am writing, an electron can revolve only in those orbits where angular momentum is nh by 2 pi. Is it clear? Where n is 1, 2 and 3 and so on. So here possible angular momentums are h by 2 pi and 2h by 2 pi and 3h by 2 pi and 4h by 2 pi and so on. So this is all about the Bohr's second postulate in atomic physics. Is it clear, guys?